One of the moons of Jupiter, known as Io, played a significant role in the advancement of 17th century astronomy. Studies had shown that in the process of crustal compression, about 100 mountains were formed on the surface, changing the landscape over the next number of centuries. The peaks of some of these, for example South Busal Mons, exceed the height of Mount Everest twice over. Along these same lines, there are vast plains on the surface of this satellite. Its surface has unique properties and comprises an abundance of colors: white, red, black, green, and even orange. This distinctive characteristic is due to regular lava flows, which can stretch up to 500 kilometers. The high density indicates that there is virtually no water on this satellite, although there have been small pockets of water accumulation found. This deficiency of water is likely due to the fact that during the formation of the solar system, Jupiter was hot enough for volatile substances such as water to evaporate from Io's surrounding vicinity, although not hot enough for this to happen on the more distant satellites. Correspondingly, often found on the satellite's surface are volcanic depressions, just like in humans, although they are called paterae. They are characterized by an even floor and steep walls. They very much resemble terrestrial calderas. However, it is still unknown whether they were formed by the collapse of the magma chamber and the collapse of the top of the volcano, like their terrestrial counterparts. Unlike similar geostructures on Earth and Mars, volcanic depressions on Io generally do not lie on top of shield volcanoes and are usually larger, with an average diameter of about 41 kilometers, and the largest, Loki Patera, is 202 kilometers in diameter. It is remarkable, but paterae often serve as sources of volcanic eruptions or far-spreading lava flows, as in the case of an eruption in the Gishbar Patera, or they themselves fill with lava, becoming lava lakes. The lava lakes on Io are covered by a lava crust which crumbles away and renews continuously. Image analysis has shown that the lava flows on Io are primarily composed of molten sulfur. However, subsequent ground-based infrared observations indicate that the flows are, in fact, composed mainly of basaltic lava and ultra-basic rock. An outstanding representative is Masubi, an active volcano on this moon of Jupiter, which is located on Io's leading hemisphere, in the Taurus region. The volcano is noteworthy for one of the largest lava flows, both on Io and in the entire solar system, covering an area of 240 kilometers. Despite the extensive volcanism that characterizes Io's appearance, most of its mountains are not volcanic in origin. The majority of them are formed as a result of compressive stresses in the lithosphere, which lift and often tilt portions of the satellite's crust, thrusting them over each other, much like giant ice flows. This is precisely why virtually all of the mountains of Io are at some stage of destruction, with large landslides being widespread at their bases. It appears that cave-ins are the main factor in the destruction of mountains. Believe it or not, but this tiny cheeseball, Io, plays an important role in shaping the magnetic field of the giant planet Jupiter. The magnetosphere of Jupiter absorbs gases and dust from the thin atmosphere of the satellite with a speed of 1 ton per second. All this matter, depending on its composition and degree of ionization, ends up in the various neutral clouds and radiation belts of Jupiter's magnetosphere, and sometimes even escapes Jupiter's system altogether. Also interesting is the fact that Io's moon is surrounded by a so-called atomic cloud of sulfur, oxygen, sodium, and potassium, which extends to a distance from its surface equal to about 6 times its radius. These particles come from the upper atmosphere of the satellite, and they are activated by collisions with particles from the plasmators and other processes in Io's heliosphere, where its gravitational strength exceeds that of Jupiter's. Io's orbit runs its course within the radiation belt, known as the plasma torus, a donut-shaped ring of ionized sulfur, oxygen, sodium, and chlorine. The plasma in it is formed from the neutral atoms of the cloud surrounding Io, which is ionized and carried away by Jupiter's magnetosphere. It's not hard to guess that Io is not at all like most satellites of the gas planets, which contain huge masses of ice, as it consists mainly of silicates and iron, like the inner planets. Further still, its interior is also incredibly active. Modeling of Io's internal composition shows that at least 75% of the mantle consists of the magnesium-rich mineral forsterite, a composition similar to that of L-chondrite meteorites. It is obvious that the ratio of the concentrations of iron and silicon there is higher than those on the Moon or the Earth, but lower than on Mars. The latest research has shown the presence of an induced magnetic field on Io, for which an ocean of magma with a depth of 50 kilometers would be required. This layer is estimated to be 48 kilometers thick. It makes about 10% of Io's mantle, and its temperature reaches about 1200 degrees Celsius. It is not known whether this 15% melting is compatible with the conditions of significant amounts of molten silicates in this inconceivable ocean of magma. Io is a bright and wondrous world, which has no equivalent in the entire solar system. Active volcanism on a satellite the size of our Moon is absolutely astounding, and the pioneering photographs of the satellite's surface, which have been obtained by a number of spacecraft, compel us to plunge again and again into the atmosphere of this distant and mysterious world.